Welcome to Cookie's Maths and Science Hub. Today we're going to be exploring the concept of bonding. Before we get into some specifics about bonding, let's remind ourselves about valence electrons. Valence electrons, or that is the electrons in the outermost shell of an atom, are essential for bonding. And we can determine the number of valence electrons of an element by looking at the Roman numeral on our periodic table, as the number of valence electrons of an element is equal to this number. Now, elements want to have a full outer shell. That is the core concept of bonding, whichever type of bonding we're looking at. So keep that in mind as we start to talk about these bonds moving forward. First, we're going to look at ionic bonding. Now, ionic bonding involves the transfer of electrons between atoms. One atom loses electrons to form a positively charged ion, and we call that a cation, while another gains electrons to form a negatively charged ion, and we call that an anion. I suggest you check out our video on ions and isotopes for more information regarding these matters. Metals usually form the cations, while non-metals form anions. That's because metals usually have smaller number of valence electrons, so it's much easier for them to lose electrons, and reverse for non-metals, they have a lot of valence electrons, so it's much easier for them to gain valence electrons. The opposite charged ions, one being positive and negative, then attract one another, creating an electrostatic force that holds the ionic compound together. And you can see that in my diagram on the right. Lithium's got rid of an electron. Now, just to clarify, we're only looking at the valence shells here. So lithium gets rid of an electron, and fluoride gains that electron, or fluorine gains that electron, becoming the lithium plus ion and the fluoride minus ion. The electrostatic forces then bring those together to form our ionic compound. When looking at ionic structures, we should take into account that they have high melting and high boiling points. They usually form a crystal lattice structure, and they are hard and brittle. Because of the fact that they are ions, they can conduct electricity well when dissolved. Otherwise, they're actually good insulators, meaning they stop conduction of electricity. And as we stated, they're held together by those electrostatic forces between the positive ions, cations, and the negative ions, anions. When naming these structures, there's 4 simple rules to follow. First, you name the metal by its element name. The metal always comes first in an ionic compound or formula. So in this example here, we've got lithium. Then you name the non-metal its element name, but change its N to ide. So it's lithium chlorine, but we change the chlorine to chloride. In specific cases, some metals, especially those transition metals, have differing oxidation states. We're not going to get too much into what an oxidation state is, but just know that's a different charge, or it makes a different cation when it forms. So you need to make sure you include those in your name as well. Finally, you need to name polyatomic ions, that is compounds that form ions, by their names. In this example, that's carbonate, CO3. Now, that might sound like a lot, but on any formula sheet you're given, it should have a good list of these ions and cations, and it's just a matter of matching up those charges to make sure the charge balances out. The charge always needs to equal 0 after you've brought compounds together. So for example, lithium has a +1 charge and chlorine has a +1 charge, therefore, -1 charge, sorry. Therefore, when they come together, that's an overall charge of 0. On the right-hand side here, I've got some different examples. Pause the video now and have a go at naming them, and I'll reveal the answers momentarily. So, for the first one, we have magnesium as our metal, and then we have oxygen, so it becomes oxide. So we have magnesium oxide. Then next, we have potassium is our metal, and we have nitrogen, therefore we have potassium nitride. We don't need to worry about including the 2 in our naming, at least not for ionic bonding. Then finally, we have calcium is our metal, and we have CO3, and yes, we gave it in the example, but like I said, it should be on your formula sheets. That's carbonate, so we have calcium carbonate. These last 2 here, I've asked you to write the formula for the name. So we have sodium iodide. You should be able to see sodium is obviously our metal, Na, and iodide is iodine, which is I, so NaI, because we can see that their charge is fine, so they easily come across. We then have potassium sulfate. So we should know our potassium is our K. Now sulfate, if you look at your formula sheets, which you should have, you'll see sulfate actually has a charge of 2-, whereas potassium is only 1+. So what that means is when we write out our formula, we're going to have K2SO4, because we need to have those 2 of that potassium there to balance out the 2 negative of the sulfate. Covalent bonding involves the sharing of electrons between two atoms. So whereas ionic is the transfer, covalent is the sharing. Atoms share electrons, once again, to achieve that stable electron configuration and form molecules. This occurs between non-metal atoms, allowing them to achieve a full outer electron shell through their shared electrons. So if we look at fluorine as another example, you can see it has 7 valence electrons. So if 2 of them come together, they can share an electron each to form a full shell for each of them. And you can see now they're sharing 2 electrons between them, making each of them have a full outer shell. Covalent structures can be split into 2 distinct groups: covalent molecular structures and covalent network structures. Covalent molecular structures are compounds containing molecules with covalent bonds, whereas network structures are a large network structure, as the name would suggest, where the bonds between atoms go throughout the entire material and are very strong. In most cases, there are some unique cases. For covalent molecular structures, they're often gases or liquids due to their relatively low melting and boiling points, whereas covalent network structures have incredibly high melting and boiling points due to their strong covalent bonds in those extensive networks, so they're usually solid and can be extremely hard. Neither of the covalent structures are very good conductors of electricity, and often, most of the time, they are insoluble in a lot of different liquids. Writing the formula for the provided names. Okay, let's go through the answers for these ones. So we have NO2, so we know our first one is going to be nitrogen, because that's the furthest left on the periodic table, and we have 2 oxygens, so it's going to be dioxide. Then we have CO2. Realistically, you've probably seen this one many a times in your science studies. It's carbon dioxide, because carbon is the furthest left, and then there are 2 oxygens, so dioxide. We then have CCl4, so again, we know our first one's going to be carbon, and then we have chlorine, or it'll become chloride, and there's 4 of them, so that's tetrachloride. Then, looking at writing out our formulas for these named ones, we have dinitrogen monoxide, so that means we're going to have 2 nitrogens followed by 1 oxygen, so N2O. Then we have sulfur trifluoride, so we're going to have 1 sulfur, because we don't need to include the mono if it's the first one, remember? And then we're going to have 3 fluoride, so SF3. When it comes to naming covalent structures, there are 4 simple rules, much like ionic. We name the non-metal furthest to the left on the periodic table by its element name, and we name the other non-metal by its element name, and once again, change it to an "-ide" ending. We need to make sure we use the prefixes in these cases. So if there's more than 1 atom of an element present, we have to say di, tri, tetra, etc. to indicate the number of that element. If mono is the first prefix, it is understood and not written. So we don't have to write mono if it's, something like CO2, which gives us the first carbon. We don't need to write mono for that one, it's just carbon dioxide. Now, let's look at some examples there. It looks like I've just given you the answer for one, but pause the video and have a go at naming some of these structures. Now again, it might seem like a lot to remember for these ones. However, it's important to realize that all this information, such as the prefix names that you can use, are on your formula sheet, or at least they should be for any test you are completing. Metallic bonding is unique compared to ionic and covalent, as rather than the transfer or sharing of electrons are still shared, but amongst what we call a sea of delocalized electrons. That is, our cations, or our positively charged ions, which are metals in this case, are floating around, bonded through some electrostatic attraction between themselves and the electrons in what we call that sea of delocalized electrons. Due to this, they have a few unique properties. They are highly electrical and thermal conductivity due to the free movement of those electrons. They are malleable, they can be easily hammered down or changed shape, and can be drawn into wires due to the mobility of the atoms within the sea of delocalized electrons. They generally have high melting and boiling points due to the strong metallic bonds, and are typically solid at room temperature for the same reason, except for mercury, which is a unique case, which is why you've probably seen mercury as a liquid before. Thanks for watching. Hopefully now you have a strong foundational understanding of ionic, covalent, and metallic bonding, as well as how to name some ionic and covalent structures. Be sure to leave a like and subscribe to the channel for future content regarding science and mathematics. Hope to see you back again soon.